For this video, we're going to cover 16.1 and 16.2. So in 16.1, we have properties of solutions. So one thing to know about a solution is you guys may have talked about homogeneous mixtures a few chapters ago. So a homogeneous mixture is something that is uniform throughout or completely mixes. Well, for our purposes, anytime we use the word solutions, we are going to actually mean homogeneous mixtures. So even though they say solutions, homogeneous mixtures are also known as, or AKA, solutions. So just kind of keep that in mind. So for chapter 15 and 16, we're only talking about homogeneous mixtures, so things that actually dissolve in one another. So that takes us to two important words to keep in mind when we're talking about this chapter. We have the term miscible versus immiscible. So miscible actually is another word we could use, would be soluble is another word. So liquids that are miscible or soluble, they're able to dissolve in one another. So an example could be, let's say salt and water. Or let's say Sprite and water. So any two liquids you can think of that actually would dissolve in one another, we can say that they're soluble or that they're miscible. They actually can mix together. Something that's immiscible, so usually if we have im, that means like not or impossible. So immiscible are going to be things that are, another word we can use is insoluble. So these are going to be things that do not mix well together. So miscible, we can think of it as mix. Immiscible, we can think of as they don't mix. So an example of something that would be immiscible could be oil and water. No matter how much oil or how much water you put, they will never be able to mix together, so they would be immiscible. So generally speaking, for chapter 16, we're only able to deal with things that are miscible, things that are actually able to dissolve in one another. Immiscible things are important, but they're hard to calculate since they're not mixing together. So when you get to the calculation part of chapter 16, towards the end, we're going to be focusing on just things that are able to mix. Okay? So the first part of 16.1 deals with properties of solutions. And so there's a few properties that we definitely want to highlight. And one of the things that they will absolutely want you to know for your quiz and for the test when it comes is factors that affect solubility. So before we even jump into that, we want to define what solubility is. So what is solubility? So solubility by definition is the ability of a solute to dissolve in 100, usually it's 100 grams of a solvent. And usually in our case, we're talking about water for the solvent. So another definition is, you could say the ability of a solute, so any substance, to dissolve in 100 grams of water is usually sometimes what we use as our solubility definition. But we're just trying to describe how well or how poorly something is able to dissolve in water. And one of the things with solubility that we'll keep in mind is that the rate that something can dissolve is actually dependent on temperature. So you might have something at 10 degrees that can dissolve just a little bit, but if you increase the temperature, you actually could increase the solubility. So we'll talk about some factors. There are three main factors that we want to keep in mind as to ways that we can affect or change solubility. So these are ways that we can increase solubility. There are three important ways. Okay. So the first one is, if we were to think about adding sugar to water, the first thing we might do is we might shake or we might stir up the mixture just to kind of make sure everything is interacting with one another. Another word that they may use is agitate. So you might shake it up, you might stir it, but you're physically trying to get the particles to interact with one another. Because if the particles don't interact, if the sugar doesn't touch the water, it's going to be hard for the sugar to dissolve. So we can mix things or stir it around to make it dissolve faster. That's one way that we could increase solubility. Another thing that we could do is we could increase the temperature. So one of the reasons why things at higher temperatures dissolve faster is, if you think of higher temperatures, we're giving it more energy, we're giving it more power to break apart its bonds to dissolve in one another. Because in order for something to dissolve, it has to break its bonds in order to mix with the solvent. So increasing the temperature gives more energy. I'll just write gives more energy to break bonds and allow for things to dissolve. And then the third thing that we can do to increase solubility is to decrease particle size. Okay, so what does that mean? So if we have, let's say, a block of sugar, so we have a cube of sugar. Okay, instead of having a cube of sugar, we could take that sugar and we could grind it up into smaller pieces and have granulated sugar and put that into water. So between these two, this one's going to dissolve faster because the particles are a lot smaller. They're easier to break apart than something that's stuck in this big block. Another terminology that they will use, instead of saying decrease particle size, because that kind of makes sense, they may actually say increase surface area. So decreasing particle size and increasing the surface area, they mean the same thing. And the reason why that is, if we look at this block here, the surface area is going to be the exposed sides, or anything that's touching the air. So I'll color in, so this part here, this part here, this part here in the front, this part here on the back, this part here on the side, and then the part on the very back. So if you imagine a box, kind of like this eraser, all the surface area would be all the parts that we can actually touch. But there's a lot of things inside of the actual eraser that we can't really touch. So there's particles inside of here that are kind of trapped. So if we were to break it into smaller pieces, so imagine if I were to break this eraser into smaller pieces, all those little particles that are stuck inside are now going to be exposed. So when we break apart the cube of sugar into these little tiny pieces of sugar, now all of these little particles have exposed areas. So we're increasing the surface area. We're increasing all of those exposed areas, which then would allow for things to dissolve a little bit faster. All right. Now, if we were to talk about, there are some terms that we have in regards to solubility curves. So I'll do kind of a rough sketch of a solubility curve and go through that. Now, one of the things to keep in mind for this quiz and test, it's going to be a lot of interpreting of graphs. So you will definitely get several solubility curves and be asked to interpret different things related to solubility. So let's say we have curve similar to this. Now for solubility curves, usually across the bottom is temperature, usually in degrees Celsius. Along the side is the actual solubility. And they will always list it in, for the units for solubility, is always going to be grams per 100 grams of water. Okay. And so what that means for solubility is we're going to try to keep track of how many grams of a solute can dissolve in a certain amount of water. And so for solubility curves, you'll end up with, let's say, curves that are like this, curves that are not as steep, so maybe do something like this. You might even have curves that are a little more even straight, where they're just kind of like that. And you might even have curves that completely shoot up even higher. Okay. So what ends up happening, the way that we would use the solubility curve, so this is they'll give you different information based off of the temperature. So again, the x-axis here is our temperature. So let's say we have a temperature of, if I mark this, let's say this is 10, this is 20, this is 30, this is 40, 50, 60. And let's say across here, this is the same 10, 20, 30, 40, 50, 60. So the way that this would work is they could say, what is the solubility at 30 degrees for, and now one of the things with these curves will represent the solubility of different compounds. So I'm going to throw in some compound names. Let's say this is HCl. Let's say this red one here is the curve for KNO3. Let's say this green is the curve for NaCl. And let's say this blue is the curve for magnesium chloride. So each of those curves will be labeled. So the question could say, what is the solubility at 30 degrees Celsius for, let's say, NaCl? So it's very simple how we would interpret this. We'd go to 30 for the temperature, which is here, and we would go up to that curve. So we kind of draw a line up to this curve, which is the green line, and then we would go over to the y-axis. So let's call it here. That's about 25 grams. Now the way that we would interpret that is, for NaCl at 30 degrees, about 25 grams of NaCl is able to dissolve in 100 grams of water. Remember, solubility is all about how much can you put in 100 grams of water. So at 30 degrees, 25 grams can fit into 100 grams of water. Okay. Now that changes if we have a different compound. So let's say instead of NaCl, we wanted to find a solubility for KNO3, potassium nitrate. Do the same thing. We're going to take that 30, go to our 30 for our temperature. We're going to go, actually let's try one that's a little bit different because that happens to be very similar. So let's say we look at Mg, magnesium chloride. So we'll go to 30, we're going to go up to the blue line here, and then we're going to go across here. So for that one, it's about 10 grams. Okay? So we went to 30 for the temperature, we went up to the curve based off of what compound they asked us to look for, and we went over to the y-axis. So sodium chloride, this one at 30 degrees could dissolve 25 grams. This one at 30 degrees could dissolve only 10 grams. So if we're comparing them, I'm sorry, this would actually be 15, because this is between 10 and 20. So this would be 15 here. So if we're comparing these two at 30 degrees Celsius, sodium chloride is a little more soluble than magnesium chloride. Now, as we change the temperature, so let's say, let me get rid of these guys here. Let's say we're not looking at 30 degrees anymore. Let's say we're looking at a different temperature, a higher temperature. Because we talked about before that if we increase the temperature, the amount of things that could dissolve should increase. So we'll test that and see if that's true. So let's look at 50 degrees. Well, at 50 degrees, if we were to go to magnesium chloride and go over to our y-axis, we're closer to 20. Let's call it 18. So here. So at 50 degrees, we're actually able to do about 18 grams. And let's compare the same thing to NaCl. We'll go up here at 50 degrees, go over to the y-axis. Now we're able to do about 25. So at 50 degrees, we're able to do 25 grams. So it is true. So one thing that we see is that as we increase the temperature, the amount that we can dissolve in the same amount of water actually increases. So the amount of water or solvent hasn't changed, but we're actually able to dissolve more solute. And this is actually how they make candy. They heat up large kind of vats or containers of water, and they're able to dissolve more sugar in it as long as it's at a higher temperature. And then when they cool those large pots of water down, the sugar clumps together and forms the hard candies. Okay? But this is in general how we would use a solubility curve. One thing we notice as the temperature goes up, all of these curves slightly increase as well. So increasing the temperature increases your solubility. It's not uncommon for you to be given a solubility curve that actually has something like, let me erase this here, that actually gives you a curve that does something like this, that goes the opposite way. Whereas you increase the temperature, the curve actually falls. If that's the case, then that means you have a gas. Gases actually are less soluble at higher temperatures. So for gases, as you increase the temperature, the solubility decreases. So if we think about why that's true, gases already are moving very, very quickly. So if we increase the temperature, we're giving them more energy to move. They're going to be more excited. They're not going to want to dissolve into a liquid. So by increasing the temperature, we're giving them more energy to actually escape. So by lowering the temperature, we actually slow the gases down. We can get them to stay inside of a liquid longer. So that takes us actually to our next point. But before we actually get there, there are some terms that we need to talk about in terms of the solubility curves. So I'm going to erase this, and we're going to keep some of that data information that we had before. So we said that for NaCl, when we compared the solubility, at 30 degrees, it was about 15 grams could be dissolved in 100 grams of water. So at 30 degrees Celsius, about 15 grams of NaCl could be dissolved in 100 grams of water. But when we increase the temperature to 50 degrees Celsius, we actually could have about 25 grams of NaCl could be dissolved in 100 grams of water. So we said that as the temperature increased, we actually could dissolve more NaCl in the same amount of water. Now, there are some terms that your teachers will want you to be able to use when we're talking about solubility curves. And I'll write them up here at the top. We have unsaturated, saturated, and supersaturated. These are descriptions that we can talk about when we talk about solutions. So at 30 degrees, if we added exactly 15 grams of NaCl, we would say that it's saturated. So let's actually do an example. So let's say we're at 30 degrees and we have 3 containers. Okay. Let's say in each of these containers we have 100 grams of water, so they all have 100 grams of water, so they all have the same amount of water. But let's say in container 1 we put 8 grams of NaCl and mix it with 100 grams of water. Let's say in container 2 we put 15. And let's say in container 3 we put 22. And again, they're all mixed in 100 grams of water, and they're all at 30 degrees Celsius. Okay, so same temperature, same amount of solvent. Now we want to assign each of these words from up here. We want to assign each of these words to each of these containers. So the way that we would do that is at a certain temperature. So again, we're at 30 degrees Celsius. So at a certain temperature, if you added the exact amount that the solubility curve predicts that the solution can take, so we added exactly 15 grams. This is saturated, meaning we added the maximum amount that we could. This guy here, we didn't add as much as we could. We could have added 15, we only added 8. This is unsaturated, meaning we could add more solute. Okay? Based off of 30 degrees, we predicted we should be able to do 15, we only added 8. This is unsaturated. This guy here would be super saturated. We added way too much than what we were supposed to. Now, this does not mean if you have a super saturated solution, that 22 grams is not going to all dissolve. Out of the 22 grams that you added, only 15 of it would actually dissolve. You'd have 7 grams of NaCl left, probably as a clump at the bottom. So we'll compare this to looking at this example over here. Now we're at a different temperature. So let's have 3 more containers here to kind of see how our terms will change. So let's say we have container 1, container 2, container 3. Okay. Let's say in container 1, and again, they're all at 50 degrees Celsius and they all have the same amount of water. Let's say we add 21 grams, 25 grams, and 31 grams of NaCl. Okay. So one thing we notice is all of these numbers are already bigger than what we started with for the first example, but that's fine, we're at a different temperature. So now, if we could have added 25 and we only added 21, This is considered to be unsaturated. We didn't add as much as we could. If we added 25, this is considered to be saturated. And if we added 31, this is supersaturated. We added more than we were supposed to. We added more than what the solubility curve said that it could take. And so one thing that we'll compare is that when we had 22 grams when we were at 30 degrees Celsius, that was considered supersaturated. But at 50 degrees Celsius, that 22 grams would be considered unsaturated. So these terms will change depending on the temperature that you're looking at, because the amount of solute you can add will change. So you always want to look at what's the maximum amount that the curve is saying that we could take. If you add less than that, then you're unsaturated. If you add more than what it says you can take, then you're supersaturated. If you add exactly that amount, then you're saturated. Another way of also defining saturated, supersaturated, and saturated in terms of solute versus solvent, we can think of it like this. When something is unsaturated, it has less solute and more solvent. So you can think of like, we might even call this dilute is another word that we might use for this. It has, so if we think of like if you're making lemonade, this example would be you have a lot of water and not a lot of sugar. So it's really watery. So less solute, but you got a lot of solvent. If something is saturated, you have the perfect amount of solute. So I'll say the right amount of solute, and you have the right amount of solvent. So it's like the absolute perfect glass of lemonade that you could think of making. You have the right amount of sugar, the right amount of lemon juice, and the right amount of water. You don't have anything that's kind of out of whack. It's the perfect amount. Super saturated, on the other hand, is almost like the opposite of unsaturated. You have more solute, so way more solute than you should have, and you have less solvent. So we might actually use a term for this and call it concentrated. So if we're doing our lemonade example, this would be an example of really, really sugary lemonade. You have a lot of sugar, not a lot of water, or a lot of lemon juice and not a lot of water. It's very concentrated. It's too sweet. So unsaturated, you're kind of below the level. You could add a little more solute. Saturated, you're at the perfect amount. You have the perfect amount of everything. Super saturated, you have too much solute. You probably want to add more water or more solvent to kind of balance things out. Okay. So then that takes us to the last point of 16.1, which deals with gases. So remember when we talked about factors of solubility, we said that we could increase the temperature to help things dissolve, we could stir it up or try to shake it up or agitate it to help it dissolve, and we could also grind up the particles, decrease the particle size to help things dissolve. Now those were factors that are really important to helping to get liquids in liquids or liquids and solids to dissolve. So we'll review those here. So we said that we can increase solubility. We can increase solubility by 1, we can stir it, so stirring. We can 2, increase temperature. And we can 3, decrease particle size. Now remember, we said if we decrease particle size, that's actually a fancy way of saying we're increasing the surface area. We're making the solute more exposed to the solvent. Okay. So these were 3 ways that we can increase solubility. Now the important thing is, this is only for liquids and liquids if we're adding 2 liquids together, or for liquids and solids if we're adding a liquid and a solid together. These are ways that we can increase solubility. Now that's not true. These do not apply when we do gases. Now if we want to increase solubility for gases, so increase gas solubility, we have different factors or different things that we could actually do. So the first thing we want to do, if we want to allow a gas to dissolve or mix in a liquid, we want to decrease the temperature. We want to slow the gas down. So decreasing the temperature, this slows the gas down. Now, the slower that we can get the gas, the more likely we can get it to mix inside of a liquid. Okay. The second thing that we must do in order to get a gas to dissolve or go into a liquid is we have to increase the pressure. Okay? So think about a soda can when we get it out of a soda machine. It's really cold and it's really pressurized. Now the reason why it's cold is because we have actually taken that carbon dioxide and gotten it into the liquid. So we've cooled it off so much that the gas has actually been trapped into the liquid. It didn't have enough energy to escape the liquid. And if we touch that soda bottle, it's usually really hard. That's because of the pressure. And when we open the soda bottle, we have that psst kind of sound. That's where we're releasing the pressure. Now, if we increase the pressure, that's forcing the gas into the liquid. But if we start to reverse these things, so if we were to have a soda bottle that's opened on, let's say, a picnic table outside in the summer, eventually the soda will become flat. And that's where all the carbon dioxide bubbles, that gas has escaped. Because you don't have the pressure, the top's off of it, so the gases are able to move about and they're able to leave the container. And if you don't have it in the refrigerator or on ice or somewhere where it's cold, then those gas particles are getting energy to be able to escape the liquid. So in order for a gas to be trapped or dissolved or soluble in a liquid, we have to have low temperatures and we have to have very high pressures. Okay. And these are things that are important for Henry's law. And Henry's law is just a calculation that we can use to predict how soluble a gas would be. But depending on the pressure, it's going to dictate how soluble a gas is. If we increase the pressure of a gas, it's going to be more soluble. If we decrease the pressure put on the gas, it's going to be less soluble. Okay. So that takes us to 16.2. 16.2 is where we start to move into a lot of the calculation portions for this chapter. We can actually calculate how concentrated something is or how dilute or watery something is. And this is where we get all those calculations in chapter 6 or 16 in section 16.2. Okay, so the first thing that we'll talk about is molarity. Okay. So molarity we usually represent with a big letter M. And it's a way for us to report concentration. So a molarity is just a concentration calculation. It's a way for us to tell someone how concentrated something is or how much we've dissolved inside of something. So if we start with an example, they could say something like, you take 10 grams of NaCl and we dissolve it in 50 milliliters of water. Okay? One thing to keep in mind, this has to be in moles and this has to be in liters. So you may have to do some conversions before you can actually use the calculation. So the way that we would do this is first we have to convert this 10 grams into moles. So if we have 10 grams of NaCl, grams are going to go on the bottom, moles are going to go on the top. This is our just basic stoichiometry. And that way, grams have to go on the bottom, so they cancel with that. Now you'd have to add up the weight from the periodic table of sodium chloride. So sodium is about 23, chlorine is about 35.5. So total, this weighs 58.5. So that would go here. And then this is for every 1 mole. So if we do that calculation, we end up with, say, that's like 0.585 moles. Now, the other issue is we have to convert this into liters. If we have 50 milliliters, we have to convert that into liters. Again, going from milliliters to liters, we move it 3 decimal places to the left. So if we're here, we go 1, 2, 3. So really it's 0.050 liters. So when we're doing our calculation, it would be 0.585 over 0.05. Okay? And if we divide that, probably about 10-ish. Now, molarity doesn't really have units, but the units could be moles per liter. And so what that is that tells us kind of how concentrated something is. Okay, so it's just moles of your solute over liters of the whole thing. Now, in our case, you would think the whole solution would be sodium chloride and water. You can always assume that the amount of solute you add is not changing the volume of the solution. So you could always just go with the amount of water for the bottom part. And sometimes what they do, to be clear in a question, they may say 10 grams of NaCl dissolves in 50 milliliters of, and instead of saying water, they may say solution, just to be clear. Okay. Now, when we have molarity numbers, we can use those to assign words like concentrated versus dilute, just by knowing the molarity number and not knowing, you don't even have to know anything about the solute or the solvent to assign words like concentrated versus dilute. So let's say we have 3 solutions. Okay. Let's say we have one that has a molarity of 0.000001, big M for molarity. And let's say we have one that has a molarity of 15. And let's say for the third solution, it has a molarity of, let's say, 300. Okay? The way that it works with molarity, the higher the number, the more concentrated it is. So out of these 3 examples, this one is the most concentrated. It has the highest molarity number. Okay? This one would be the most dilute. It has the smallest number. Okay? So very small molarity numbers means that the solution is dilute. It has a lot of solvent or a lot of water in it. Things that have very high molarity numbers means it's very concentrated. It has a lot of solute. So we can say that it has lots of solute by being concentrated, and this has lots of solvent by being dilute. So a lot of water. So for our lemonade example, this would be something that's very watery, like watery lemonade. This would be very sugary lemonade. Okay. The other equation that's important in this section are dilution equations. So if we want to dilute something, we want to make it less concentrated. We want to make it more watery in a sense. So let's look at that dilution equation. So dilutions. If we want to dilute something, we want to make it less concentrated. So dilution just means we want to add more solvent. And the reason why we want to add more solvent is we want to make the solution less concentrated. Okay? Now there's a calculation that we can use to figure out exactly how much solvent or water that we need to add to make something more dilute. Okay? And it looks like this. M1V1 equals M2V2. Okay? So this is our initial molarity, initial volume, final molarity, and final volume. So the way that this calculation could work is, let's say we have a solution that has, so I'll write it out. Okay, so we would have something kind of like this. Okay, so The way that this would work is if we have 300 milliliters, so this is a volume calculation information, this is going to be our initial volume. We have it at 3.5 molar, that's our initial concentration. But we want to dilute it, we want to add more water or more solvent to get it to this concentration. So this is our M2. Okay? So what we have to find is our V2. So we have M1, V1, we have M2, we just don't know what our final volume would have to be. So the way that we would set this up is, just be careful, this volume has to be, the volume actually does not have to be in liters, just be consistent. If it's milliliters on this side, that means your V2 will be in milliliters. You just want to make sure you're either milliliters for both V's or liters for both V's. So the way that we would do this is the initial molarity is 3.5. Our initial volume is 300. I'm just going to keep it in milliliters. Equals our final molarity is 2.7, and we don't know what V2 is. So all we would have to do is divide by 2.7. So I don't have a calculator, but this looks like to be about, so this ends up being 1050 over 2.7, which is about, let's call it like 330. So like 330-ish, but if you have a calculator, you can find the exact amount. So what that tells us is this value that we just found, that's our V2. Okay? So our initial volume was 300, but our final volume is 330. So what did we actually do to dilute it? We actually added 30 milliliters of water. So if we notice, the volume started at 300, but now the final volume is 330. So the difference between those is how much solvent we added. So if we started with 300, but we ended with 330, we actually added 30 milliliters of water. So for these dilutions, we're always adding water. So when the volume changes, the difference in the change is the amount of water that you added. So we added 30 milliliters of water. So depending on the question, they may want this is your answer, or they may want this is your answer. So the difference between them would be, if the question said, what is your final volume? So this is your initial volume, initial concentration. This is your final desired concentration. The question could say, what is your final volume? In that case, we'd put this answer. But if the question says, describe how you would get this new molarity, then this would be your answer, because we're describing what we would do. Well, we would add 30 milliliters of water. And why do we know we need to add 30 milliliters of water? Well, because if we want this concentration, we have to have this volume. And in order to get this volume from what we started with, we would have to add 30 milliliters of water. So just be very careful with how they ask the question. If they want the final volume, we just go with 330. If they say to describe how we would get the concentration that we want, we would have to put a little more words to it and say add 300 or add 30 milliliters of water. The last thing in this section is percent solutions. So there's a couple different ways that we can also report concentrations. We can report them in terms of molarity, like we talked about. The next two are two different ways that we can also report concentration. So one is not better than the other, they're just different ways of reporting kind of the same information. So we can do percent by mass, okay, or we can do percent by volume. And if we start with percent by mass, so what that would just mean, if we're doing a calculation, we would want to do grams of the solute over the total grams. And then times 100. Okay? If we're doing percent by volume, and a lot of times we see percent by volume in like wine or beer bottles, it may tell us how much of the alcohol is in the total volume, but we can do, for volume, we use milliliters or liters, so we can do milliliters of solute over milliliters of solution, which would be the whole thing, times 100. Okay? So if we do two quick examples, let's say we took 10 grams of NaCl and we added it to 300 grams let's say we added it to 90 grams of H2O. And the question may be, what is the percent by mass of NaCl? Okay? Very simple calculation. Grams of solute, this guy is our solute. The 10 grams is our solute. So we just do 10 grams over the solution. Solutions are always your solute and your solvent added together. So I'll write that. The solution is always your solute plus your solvent when we're doing these calculations. So you would need to know what both of those are. Okay? So all we're going to do, we're going to add our solute, that's 10 grams, plus our solvent. Our solvent in our case is water, 90 grams. So we get 10 grams over 100 grams times 100. Our grams would actually cancel out. We end up with 10%. So by mass, 10% of the total mass is coming from sodium chloride. That's how we would interpret that number. So 10% of the whole mass of the solution is sodium chloride. The other 90% would be water. Okay, if we look at a percent by volume example, let's say we had 30 milliliters of KNO3 and we had 70 milliliters of water. And they want to know what's the percent by volume of, let's say, water. Actually, percent by volume, usually they only ask for the solute, okay, of KNO3. So we tackle it the same type of way. We're going to put the volume information for KNO3 at the top. So that's 30 milliliters over. Now we said solution is always solute plus solvent together. So we want to do 30 milliliters plus the 70 milliliters. Okay? So we would then get 30 milliliters over 100. The milliliters could cancel out. You don't need that unit. Times 100. So 30 over 100 is like 30%. Okay? So the way we would interpret that is 30% of the whole solution is KNO3. So 30% of the total volume is coming from KNO3. So these are just, again, two other ways that we can report concentration. So we can either do percent by mass or percent by volume. Okay? So in the next video, we'll go into some more detailed calculations involving colligative properties and mixtures.